Hi everyone, in this video we're going to be talking about vectors and their applications. We're going to be specifically looking at geometrically defined vectors, so like drawings of the vectors and how we can use those. And then in the next section we'll talk about algebraically defined vectors. So we'll start to use algebra to figure out things about vectors in the very next section. We'll start with some basic terminology that's going to come up when we're talking about vectors. So a scalar, just think of it as a number. It's specifically going to represent the magnitude of a quantity, but it's just going to be, just like we've been dealing with for a very long time, a number. A vector is in 2D space or the xy plane, and it's a directed line segment. So it's basically a line that's pointing somewhere. You can think of like an arrow, and it has a length associated with it. So here's an image of a vector. So the name of this vector is vector OP because of where it starts and stops. In 2D space, in 2 dimensions, it starts at point O. So this starting position would have like x comma y as the starting point. And it ends at a different point in space, which is we're calling P. And so the name of this vector is vector OP. Where it starts is called the initial point, and where it ends is called the terminal point. A couple of ways that you'll see vectors written is either with bold print or with this little arrow on top. Both of these mean a vector. For us, we're going to usually see bold print, but feel free to use the arrow on top. The magnitude is the length of the vector, and our notation for that has these vertical bars. Hopefully this looks familiar, like absolute value. So this is the length of your vector, so however long it is. It's called the magnitude. So you can call it length if that helps you understand it or remember, but we're going to refer to it quite a bit as magnitude. So two vectors are equal if and only if they have the same magnitude in the same direction. And I'll show you some images on the next slide. Okay, so these two vectors are not equal, and based on what we just talked about, hopefully you can see why. It has to do with the way they're pointing, their direction. So vectors OP and PO, they have the same magnitude or length, but they're pointing in opposite directions. So this is our notation for magnitude. The magnitudes are the same, but they're pointing opposite, and so actually vector PO is negative vector OP. So when it's exactly pointing 180 degrees away from the previous vector, and it's the same length, it's actually the opposite, and we're going to get into that later. It's called the equilibrant vector. All right, so here's some examples for you to start to just consider when vectors are equal or not. So taking a look at vectors A and B, before I show you, think about, are these equal vectors? Well, yes, they point the same way, they have the same direction, and they're exactly the same length. So their magnitudes are equal. So these vectors are equal. Notice I'm using bold print to denote vector. You could use the little arrow on top if you wanted to as well. C and D, these two vectors, they're also equal. They have the same direction and the same length or magnitude. Okay, now take a look at vector E, and I want you to compare it to vector A. It looks like it has the same magnitude, like vector A and vector E look like they're about the same length, but E is not pointing in the same direction as A, so vectors A and E are not equal, even though they look like they have the same magnitude. And now take a look at vector F and compare it to vector A. They are pointing in the same direction, but because F is shorter, it's not the same length, vectors A and F are not equal because they don't have the same magnitude, even though they point in the same direction. Now, some of the things you're going to do with vectors is add and subtract them. So starting with the sum of two vectors is also a vector. So when you add two vectors, the result of the sum is actually called the resultant vector. So here's two ways to add vectors. So in these two images, what you would know at the beginning is vector A and vector B. And then what you would compute or draw is the resultant, vector A plus B. So there's two ways to get the same resultant. On the left, what we do here is we start with vector A, and then at the head of vector A, you put the tail of vector B, and then you line up, so you start back at the initial point for A, and you just draw a vector connecting the initial point of A to the terminal point of B. So from tail of A to head of B, that's the resultant of A plus B. The other way to do it is called this parallelogram method. And so what you do is you take vector A, you just draw it, and then you take vector B and you line up the tail of vector B with the tail of vector A. So you line up the two tails of the vectors, or the initial points. And once you do this, you just roughly draw a parallelogram, and then the diagonal from the meeting point of the tails of the vectors, or the initial points of the vectors, the diagonal to the end of the parallelogram here is also the resultant. So these are the same exact vector, A plus B, just two ways to get them. The sum or difference of two vectors. Okay, so when you're subtracting another vector, technically you're adding the opposite. So let's start with the sum of vector v and its opposite, negative v, is 0. Think of it just like with numbers. If you have a number and then you add its negative, you're going to get to 0. So the magnitude of that result or resultant is 0, length 0, but it's technically a vector. So if you're adding two vectors, your answer is a vector, so it's the 0 vector. Even though it's just 0, it's technically the 0 vector. And so when you want to subtract vectors, you officially actually add the opposite of the vector you're subtracting. And so instead of me saying like a minus b, this is a plus negative b. So what I would know at the beginning of this problem is I would know what vector a is. I would know its magnitude and length, or its magnitude and direction. I would also know vector b. And so using the parallelogram method that we just went through, if I line up the tails of the two vectors that I know, well then after I know vector b, I actually draw its opposite. So negative b, same length as b, but it points exactly opposite, or 180 degrees opposite of where b points. And then I draw my parallelogram with a as one of the sides and negative b as the other side. And so I form my parallelogram, and where the two tails of the vectors meet, the two initial points, that's where I draw my diagonal resultant vector. So this magenta colored vector is the resultant a plus negative b, or technically a minus b. Now a scalar product of a vector, it basically is just going to change the length, but also if you multiply by something negative, it could change the direction. So a real number k times a vector u, and notice the vector is in bold print just to help you recognize that it is a vector. When you multiply a vector times a number or a scalar, it's going to change the magnitude. And now it changes it by that multiple, a k multiple of whatever the magnitude originally was. So let me explain. Let's say our original vector u over here in black has magnitude 3. Just pretend it's 3. If I were to times it by scalar 2, so like k is 2 here, then this length of my new vector in blue would be 2 times 3, so this would be length 6, and so on. So let's go back and say u is length 1, so then 2u would be length 2, and then 3 halves u would be 3 halves, or 1.5 in length. And so it depends on your initial length, whatever the original magnitude is. When you times your vector by a scalar k, it just multiplies the original magnitude by that amount. Now, drawing-wise, so geometrically, if you look at how long u looks in a drawing, in our visual here, when you draw 2u, it should look twice as long. When you draw 1/2 u, it should look half as long as the original. Now take a look at this last one here, negative 2u. So the 2 times u is changing the magnitude, it's doubling the magnitude of the original vector, but the negative also changes the direction that it points. So notice we already had 2u, so we knew that length. So notice the purple is the same length as light blue, but because it's a negative, it changed the direction that the vector was pointing by 180 degrees. So it's pointing exactly the opposite direction that u was pointing. Let's discuss some properties of parallelograms, because we're going to end up using these in some problems that we try. So some reminders from geometry about parallelograms. A parallelogram is a quadrilateral whose opposite sides are parallel. The opposite sides and opposite angles of a parallelogram are equal, and adjacent angles of a parallelogram are supplementary. So we're going to use this supplementary fact in our next example. And then the diagonals of a parallelogram bisect each other, but don't necessarily bisect the angles of the parallelogram. Let's take a look at our first example here. Two forces of 15 and 22 newtons act on a point in the plane. If you have any physics in your background, some of these questions might start to sound somewhat familiar. If you don't, that's perfectly fine. We're going to go through how to solve them. Now, two forces, the forces, we're going to draw them as vectors. Vectors are going to be used to represent the forces. And a newton is just a unit of force. So it's about 0.225 of a pound. That's not going to affect our answer. We're just going to put newtons on the answer that we get. Now, if the angle between the forces is 100 degrees, so if I draw my two vectors representing these forces, the angle between them is 100 degrees. Find the magnitude of the resultant vector. Or another way to say this, find the length of the vector that you get from adding those two force vectors. Now, no drawing is given, but we're going to come up with a drawing, and I recommend when you get problems like this to try to draw it out first. It's probably going to help you in solving. So here's our drawing, and it really doesn't matter how you start, you just want to be consistent. If I draw my 15 Newton force going to the right, then I can't draw my 22 Newton force also going to the right. It has to have this angle of 100 degrees between it. So that's all I mean by being consistent. I could have started with my 15 unit force going downward. But in any case, so my 15 unit force, Newton force, is, for me, going to the right. I'm calling it vector PQ. And so 100 degrees away from that, I'm going to draw vector, what I call PS, which is my 22 Newton force. Okay, so I have my two vectors. They have the same initial point, so they both are acting on this point P in space, or in 2D space. There's 100 degrees between them, and I know their lengths, 15 and 22. So now we have to figure out some other things. How are we going to answer this question? Well, the resultant vector, which is what we were asked about, is the diagonal if we form our parallelogram here. And so we have already these two vectors meeting at the point P, so it's already ready for us to draw the parallelogram. So you would just, from the head of PQ, start to draw your parallelogram, and it would meet up with, from the head of PS, down here. And so the diagonal from the initial point across the parallelogram is our resultant, which I'm calling V. And so now we're going to use one of the facts we just talked about from our parallelograms. The angles of a parallelogram, in this case adjacent to P, both measure 80 degrees. And that's because we just talked about, for a parallelogram, adjacent angles are supplementary. So that's because at point P, we know that angle is 100 degrees. So the angle on the same line, or in this case same vector, is supplementary. So it has to add up to 180. So this point, at point Q, this angle has to be 80. Same thing over here. If I'm at point P, the angle is 100 degrees. So going down this vector adjacent, this angle has to also be 80 because it has to add up to 180. Now, we're going to use our law of cosines with either triangle that we just formed. So law of cosines, we just learned that in the previous video, and this is one of our three versions of our law of cosines. If you have your triangle with angles ABC and your side lengths little a, little b, and little c, then this is your law of cosines. Now let me just mention what this is saying, because none of our letters kind of add up here with what the lettering we've used in the past. But let me just clarify. So law of cosine says if I have two side lengths that I know, b and c, little b and little c, then I can use those two known side lengths and the angle capital A between them. So capital A in this case would be the angle between sides b and c. I can use all of that known information to find the last side, side little a. And so this is exactly what we have. We know a side length 22 newtons. We know another side length of a triangle, 15 newtons. Now you have to kind of pick which triangle you're going to work with. You're going to get the same results, but let's just focus on the bottom half. So this side length of this triangle is 22. Down here, it's a parallelogram, so this is also 15, just like the top was 15. And then the angle between them is 80. So in our case, b, little c is 15 and 22, and then capital A is 80. So we fill in what we know into our law of cosines, and we just are going to use absolute value here because it's representing magnitude or the length of the vector. That's what we're looking for. And so we fill in our values, and then we're going to solve for v. Okay, so you would use your calculator here, and you would get that the magnitude squared, or the length squared of the resultant vector v, or this side of our triangle, is about 594. So when you take the square root, the magnitude of our resultant vector is about 22, or in this case 22 newtons. Okay, and the number should kind of make sense. If we got something like 24,000, something would have been off with our calculations because of the vectors we were working with. This was only 22 newtons, this other one was only 15. So this is a relatively number close to those, so it does make sense. So the magnitude of this vector is 24 newtons. Let's discuss the equilibrium for a moment. We did kind of touch on it at the beginning of the video. So sometimes it's necessary to find a vector that will counterbalance a resultant. So think about what that means real quick. Counterbalance. So if you have a vector, it could be like the sum of two forces like our previous example. Let's say you want to counterbalance it or offset it. You want to find the force that would negate it or make it exactly zero when you were to add them. And we discussed if you add v plus negative v, you get the zero vector. So the equilibrant is this opposite vector and the vector with the negative sign. So if you're starting with a vector that we call u, its equilibrant is just negative u, or its opposite vector is just negative u, and they counterbalance each other. So we're going to use this in an example here. So find the magnitude of the equilibrant of forces of 48 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. So far this is similar in setup to our previous example. Then find the angle between the equilibrant and the 48 Newton force. So the difference so far is that we're dealing with the equilibrant, not the resultant. The resultant would be if we add up the 48 Newton force vector plus the 60 Newton force vector. But we do want to add those up, but then we want the opposite. We want the equilibrant. So that word is just meaning we want the opposite vector. So here's our drawing. We have a 48 Newton force, which is this vector ending at point B. We have this 60 Newton force vector ending over here at this bottom point, but they both have the initial same point. So the starting point is the same for both vectors. We are told that the angle between them is 50 degrees. Okay, so at this point A, our initial point, this is 50 degrees between the two vectors. Now in the last example, we were finding the sum or resultant of those two vectors. But this example wants us to go a step further and find the equilibrant, so the negative or opposite vector of that resultant. And then also a little bit extra, find the angle between the equilibrant and the 48 Newton force. So the second half of this question is asking you about this angle alpha. Here's the equilibrant, negative v. Here's our 48 Newton force vector. And so alpha is the angle between those two vectors. So that's going to be the second part of the problem. So the equilibrant is negative v. And then the magnitude of the equilibrant is the same as the magnitude of this original v, this resultant of adding these two force vectors. It just points the opposite way, but the magnitude is the same. It's the same length. So using our law of cosines again that we used in our previous example, we know one side length of a triangle here is 48. Now, you kind of have to pick which triangle you're working with. I'm going to work with the top. The other side length of a triangle is 60, and then the angle between them is 130. Okay, so think about for a moment how I knew this was 130. We talked about it in our last example. Since this is forming a parallelogram, when we have this resultant vector as the diagonal, the angles in the parallelogram on the adjacent side are supplementary. So the fact that this one was told to us that it was 50, then this one has to add up to 180, so this must be 130. So then my one side length is 48, my other side length is 60, and the angle between is 130. So that's where we get these values for our law of cosines. So we fill them in and we find out what V is, the magnitude of V. So V squared is about 9,606.5. So V is about 98 newtons. And so the question was, find the magnitude of the equilibrant. Well, the magnitude of V is the same as the magnitude of negative V. So the magnitude of the equilibrant is actually the same thing as we got, so 98 newtons. Okay, so the second half of our question was asking about the angle, what we called alpha, between the equilibrium vector and this 48 Newton vector. And so how do we find this? Well, we basically just have to figure out what do we know and how can we use it to get this angle. Now, notice that we know 50 degrees is this entire angle at A, but we don't really want the entire thing. So what we're going to do instead is recognize that part of that angle that adds up to 50 degrees can be used to help us. So angle CAB, we're going to end up subtracting it from 180. So let me just clarify what angle CAB is. CAB, so A is where the angle is being formed at, but it lines up with points C and B. So it's this angle here. Okay, so this is angle CAB. It's like the top half of the 50 degrees angle. And so what we're going to do, and here's why we're going to subtract it from 180. The whole vector V and its equilibrant lie on a line. So we know that this would be a 180 degree angle. And so alpha is part of that. It would be 180, but there's this little piece, CAB, that we have to take away because we know it's not exactly 180. There's a little bit less than that we need to take away. So now we go back and we use our law of sines. So angle CAB is this little piece here, and law of sines says I can take sine of my angle and divide it by the length of the side across from it, which is 60 in this case, and the ratio stays the same for any angle I do that with in my triangle. So I just pick another angle that I know. Well, I know angle B is 130 degrees, so the side across from 130 degrees is V, the resultant vector. So 130 degrees is here at angle B. Across from it is side V, which we figured out was 98 in length. That was the resultant magnitude. And so we just use our law of sines to figure out the missing angle. And so we're just going to solve for sine CAB and then take sine inverse. Okay, so when you times both sides of this proportion by 60, we get that sine CAB is about 0.469. And so if you take sine inverse, you get that the angle, this little angle piece that we need, is about 28 degrees. And so we know, again, this whole angle lies on a line, so it's 180. So we just say 180 minus this little piece in red, which was 28 degrees, gives us our missing angle alpha. So the angle between the equilibrant and our 48 Newton force is 152 degrees. Let's take a look at this next example. Find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal, and assume that there's no friction. So you have this wagon on a ramp, and the ramp is inclined at 20 degrees, and you're trying to figure out, well, how much force do I need? Like, if I were to stand here and hold this handle, how much force would I have to exert, and in which direction to keep this wagon from going backwards, back down the ramp? And so the drawing, let me explain all the parts to this, why I have these other vectors here. But basically what you're looking for is this vector BF, the magnitude of it, because that's going to represent the force that you're looking for. Notice the way it's pointing is up the ramp, so it's the force needed to keep this wagon from going back down. So starting with the vector BA, it's directly vertical, so straight down. This is the force due to gravity. And then BC, this vector, is perpendicular to the ramp. So notice the edge of your ramp here, and then 90 degrees away from that is this vector that I'm calling BC. And it's the weight that pushes against the ramp. And now what we have here is a triangle that we can form using some vectors. So we know about vector BA, that's going to be 50 pounds for the force. But we can rewrite that as the sum of these other two vectors, and that's going to help us figure out some values, because now it's a triangle that we formed, a right triangle. And so this vector BA is actually just the sum of vector BC, this vector perpendicular to our ramp, plus AC, but pointing the other way, so negative AC. So this little edge of this triangle that we're using. Why we're interested in AC is because that's actually going to be parallel to the vector we're looking for, this force vector BF. And it's the same length as well as of what we're looking for. So that's going to help us out. So vector BF represents the force that would pull the weight up the ramp. So again, this is the vector we're going to be looking for, BF, the magnitude of that, because it's going to be how much force we need to apply to keep the ramp not going back down. And then since vectors BF and AC are equal, notice these two vectors are equal, the magnitude of AC is going to be the magnitude of BF, which what we're looking for. So again, we're basically using information we do know something about to figure out the thing we don't know a lot about. And so we're using this triangle that we formed. We're going to figure out some stuff about vector AC, and that's going to tell us about this vector BF that we do want. So vectors BF and AC are parallel, and because of that, the measures of angle EBD equals the measure of angle A. So let me identify for you real quick. Angle EBD is this angle right here. So it's outside the blue. So angle B is technically inside the blue triangle, but angle EBD is outside the blue triangle. It's right here. And my claim to you is that that angle equals this angle down here, A, inside your triangle. And I said because they're parallel vectors, and here's why. You have alternate interior angles formed. So the ramp is parallel to this edge of our triangle, which is formed with vector AC. And these angles, which this one's EBD and angle A, are alternate interior angles. So they are going to be, in fact, equal in measure. Now, since angle BDE and angle C are both right angles, so this angle here, and then this one down here, and then we have two angles that we figured out earlier were equal, we now know that our two triangles are similar triangles. So we have two triangles, one's formed on the ramp, and this other one was formed down here using our vectors, and they're similar. So we can use information that we know about one to figure things out about the other. And so therefore the measure of angle ABC is equal to angle E, which was told to us it's 20 degrees. So this little wedge of an angle is 20 degrees, and it's because of the similar triangles that we just formed. We were told that this angle was 20 degrees from the incline of the ramp, and so this angle here is 20 degrees. And we now know quite a bit of information about this right triangle that we formed with our vectors. And then we're going to use that to figure out this force vector that we need to keep the wagon from going back down the ramp. So from our right triangle, this right triangle here that we formed with our vectors, right triangle ABC, we know that sine of angle 20 is going to be opposite side over hypotenuse. So magnitude of AC, or length of side AC, divided by 50. And so magnitude of AC is about 17. So the force that we need is about 17 pounds to keep the wagon from sliding down the ramp. So this side of our triangle was this vector AC, which we figured out was about 17, in this case pounds, and that's going to be the same amount of force that we need right here for this vector to keep the wagon from moving. Let's take a look at this next example. It's similar to the one we just finished, so it'll go a little quicker because we just went through all that work to figure out how to set something up where we have forces acting on an object on an inclined plane. So a force of 16 pounds is required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? So very similar to the wagon problem, but there's just a missing drawing of a lawnmower here. But the difference is we don't know the angle of the incline, so we don't know how high up this ramp is pointing. We do know some other things, and we started to form this right triangle with our vectors. Vector BA is the force of gravity, in this case the 40-pound lawnmower. And then vector BC is perpendicular to our ramp, our inclined plane. And then vector AC is the force required to hold it up. So technically vector AC is the same as vector BE up here as far as its magnitude and direction. BE would be the vector holding the lawnmower up, but it's the same as this vector down here. So we know that this is 16 pounds. Okay, so notice what we have to work with. We have a right triangle and we have two side lengths. And from our last example, we know that this triangle that we formed with our vectors is similar to this triangle on our inclined plane. And so vector BE represents the force required to hold the lawnmower on the incline, which we just talked about. And then in our right triangle, ABC, the measure of angle B, which is this little wedge angle up here, is equal to angle theta, from our similar triangle situation from the last example. The magnitude of BA represents the weight of the mower, which is 40 pounds, and then vector AC equals vector BE, what I was just mentioning a moment ago. Okay, so we're looking for, if you can figure out where we're going, angle B, because it's going to be the same measure as angle theta. So sine of B is opposite side over hypotenuse side of our right triangle. So 16 pounds over 40 pounds. So sine B is 0.4. Sine inverse gives you that B is about 26 degrees, and that is the same as angle theta. So this inclined plane or hill makes about a 23.6 degrees incline with the horizontal. The next examples that we're going to get into have to do with airspeed and ground speed of a plane. So we're going to discuss that first and then get into the example. So first, the airspeed of a plane is its speed relative to the air. The ground speed is the speed relative to the ground, and they can differ. And so the ground speed of a plane is represented by the vector sum of the airspeed plus the wind speed. Okay, so here's a drawing. If you think of right here on this reddish colored vector, you have a plane with the bearing and airspeed. So your plane is trying to travel in this direction, but there's wind acting on it, a force vector representing wind acting on your plane, pushing it, in this case, kind of to the left. Okay? And so your ground speed and direction are actually represented by this vector. So from the ground, it would appear that the direction the plane is going is what we have in blue here. And that's because the plane might be trying to travel this direction, but the wind is acting on it and forcing it to travel this direction in blue. So for this example, an airplane is following a bearing of 239 degrees at an airspeed of 425 miles per hour. It encounters a wind blowing at 36 miles per hour, and that wind is coming from the direction of 115 degrees. So the question is, find the resulting bearing and the ground speed of the plane. So there's a lot going on here. We're going to try to draw it all to figure out the answer to the question. But real quick, a reminder on bearing. If there's no direction given, like north, east, or southwest, or something like that, it's assumed from due north. So this is saying from due north, you go clockwise, 239 degrees. Same thing over here for 115 degrees from due north. So we're going to draw two separate compasses with our north, south, east, and west arrows. One for the airplane and its airspeed, and then the other one for when it encounters the wind. Okay. All right, so here's what we have going on. On our right side here, we have from due north traveling 239 degrees clockwise, and that's the bearing of the airplane. Okay? And its speed is represented by the magnitude or length of the vector in blue, which I'm calling little c. Now, our second compass, north, south, east, west, is going to be when it encounters the wind. So right here at this point is when it encounters this 36-mile-an-hour wind, and the wind's direction, so from due north, is 115 degrees, and it meets the plane right here, and then it's like, think of it like pushing the plane that direction. And then the speed of the wind is represented by the length of this vector A. And so the actual bearing of the plane is going to be this direction that green, vector B, is pointing. And then the magnitude of this vector B in green is going to be the ground speed of the plane. So we have a lot to figure out here, but this is the first step, figuring out the drawings based on the given bearings and magnitudes. So vector C represents the airspeed and bearing of the plane. That was the blue vector. Vector A represented the wind speed and direction. And then we want angle ABC because it's going to help us find this vector B that we're looking for. So angle ABC is this angle right here in the middle in this triangle that we formed with our vectors. And so the way that we're going to figure out this angle ABC is to break it apart into two separate angles that we know some things about. So it's the sum of this blue angle, A, which I'm calling A, B, N1, plus the red angle, which is N1, B, C. So we're going to separate this into two steps, well, a little bit more than two steps, but two angles to figure out the whole angle, ABC. So angle SAB measures 239 degrees minus 180 degrees. So that's way over here, and I'll show you why we need this. So over here, we know that 239 degrees is how we got to this airspeed vector. Well, if we take away 180, this straight line, so this is 90, 180, if we take that away from 239, the leftover is this measured angle 59 degrees. So why we want that is because our blue angle is actually 59 degrees as well, because we have alternate interior angles. There are two parallel lines here, the north-south line over here and the north-south line over here, and they're cut by this blue transversal. And so this angle in blue is an alternate interior angle to this 59 degree angle. So we're halfway done. We found out that this one is 59 degrees. So now we have to figure out this other angle on the left side over here. So angle E1BF measures 115 minus 90 degrees. So that's right over here. E1BF. Okay, why we want this one is because it's going to help us if we go across. This is a vertical angle. Okay, so if we know that this, so real quick, 115 all the way to the red vector, the dotted part, and if we take away the 90 degree part of it, we have 25 degrees left over. So we know that if this is 25 degrees, then because this is a vertical angle to this angle 25, this measure is also 25 degrees. Okay, and now if we know that that's 25 degrees, well, if we just say, well, they complement each other if I take the 25 degrees and the angle I was looking for. Okay? So the angle I was looking for was the complement of 25. So we just do 90 minus 25, and this other piece of our angle was 65 degrees. All right, so we found the two individual angles. So if we add them up, 59 degrees plus 65 degrees, we now know that angle ABC is 124 degrees. Now we're going to use our law of cosines to find the magnitude of that vector that we were looking for the ground speed. We had formed a triangle that we just found the angle with, and then we knew two side lengths for our triangle based on the speed of the plane and the speed of the wind. So just a reminder, our law of cosines. And for our particular example, we're just going to use our lettering from our image. Side A was the wind speed, side B was the airspeed, and then angle ABC was that angle we just worked so hard to figure out. And then we fill this in to our formula for law of cosines, and then using your calculator, you'll figure out that B squared is about 199,032. So B is about 446 in magnitude. Okay. And so now to find the resulting bearing of B, we must find the measure of angle alpha. We found the magnitude, but we also need to know the bearing. So we're almost there. This would represent the ground speed, 446 miles per hour. Now the angle alpha, let me remind you what that looked like in our image. So in our image, alpha is the difference here between our airspeed vector and our ground speed vector. So we knew that the airspeed vector was at a bearing of 239 degrees, but then the wind pushed it a little bit further to give us our ground speed vector. So we need to find this difference, this angle alpha. Okay? And so we have our law of sines. We know that sine alpha, sine of that angle alpha, if we divide it by the side across from angle alpha, which was 36, the ratio is equal to that of sine of the angle we worked hard to find, 124 degrees, divided by the magnitude of the side across from it. So that was the length of the green vector that we just found. Okay, angle 124 was across from side 446, the green vector. And then we just multiply both sides of this proportion by 36 degrees, or sorry, 36. And then we solve for alpha, and we do sine inverse, and we get that alpha is about 4 degrees. So we already had a bearing of 239 degrees, and we just go a little bit further over from the wind, add 4 to that, and so the resulting bearing is 243 degrees. So you can say the ground speed of the plane is 446 miles per hour, and the bearing is 243 degrees.